Assalamualaikum and hi everyone. Hopefully you are doing great today. Today we are moving to a new chapter, chapter 6, stability. For your information also, chapter 6 is the last chapter to be covered for this course. Here are the learning outcomes that should be achieved by the students at the end of this chapter. At the end of this chapter, students are expected to be able to generate a root table, interpret the root table, and use a root table to determine the stability of a system. This chapter will take about 3 weeks to be covered. So, this week lecture will only cover part 1 of chapter 6. We will start this chapter with some introduction about the stability of a control system. And we will also learn how to generate and interpret a basic root table in order to determine the stability of a system. So, let's begin our part 1 of chapter 6 lecture. In this chapter, we discuss about stability in designing a control system. Remember, there are 3 requirements into the design of a control system. The first requirement is transient response. The second requirement is stability. And the third requirement is steady state error. So all of these are the 3 requirements when designing a control systems. Previously, we have covered about the transient response. So for today's lecture, we will discuss about the other requirement, which is the stability. Stability is the most important system specification. If a system is unstable, the transient response and the steady state error are moot points. Then, what is stability? There are many definitions of stability depending upon the kind of system or the point of view. For this chapter, we will take a look on the stable, unstable, and marginally stable control system, and we limit ourselves to linear, time invariant system only. This slide relates the stability condition with the force and natural responses. You may read this slide by your own later. First, what is a stable system? How do we determine if a system is stable? Recall from our study about the system poles. If the closed loop system poles are in the left half plane of the S-plane, hence the system is stable. In other words, the stable system have closed loop transfer function with poles only in the left half plane. Again, the stable system have closed loop transfer function with poles only in the left half plane. Figure A shows an example of the unit step response of the stable system. From the unit step response, we can see that the oscillation for the stable system diminish as time approach infinity. Physically, an unstable system can cause damage to the property, to the system, and even to human life. Then, what is unstable system? From the perspective of system poles, unstable systems have closed loop transfer function with at least one pole in the right half plane of the S-plane and a pole of multiplicity greater than 1 on the imaginary axis. Thus, If the closed loop system poles are in the right half plane of the S-plane, hence the system is unstable. Figure B shows an example of the unit step response of unstable system. From the unit step response, we can see that the oscillation for unstable system increase without bound as time approaches infinity. Finally, the marginally stable system is defined as a system that have closed-loop transfer function with only imaginary axis poles of multiplicity 1 and poles in the left half plane. The response neither increase nor decrease in amplitude. The response of the unit step is neither increase nor decrease in amplitude. Figure shows the plots of stable, unstable, and also marginally stable unit step response. Remember, the oscillations for stable system diminish as time approaches infinity. The oscillation for stable system diminish as time approaches infinity. The oscillation for unstable system increase without bound as time approaches infinity. And the oscillations for marginally stable system is neither increase nor decrease as time approaches infinity. Figure in the slide shows the difference between S-plane and Z-plane. S-plane is used to plot the zeros and poles of the Laplace transform. Meanwhile, Z-plane is used to plot the zeros and poles of the Z transform. For the Laplace system, the system is considered stable if it has closed-loop transfer function with poles only in the left half plane of the S-plane. And for Z system, the system is considered stable if it has closed-loop transfer function with poles only in the unit circle. In this section, we learned a method called a Routh-Hurwitz criterion for stability. We learned a method called a Routh-Hurwitz criterion for stability that yields stability information without the need to solve for the closed-loop system poles. Using Routh-Hurwitz criterion, we can know how many closed-loop system poles are in the left half plane, in the right half plane, and also on the imaginary axis. Basically, the Routh-Hurwitz criterion requires two steps. The first step is to generate a root table, and the second step is to interpret the root table. Therefore, in this section, we will generate and interpret a basic root table. In the next section, we will consider two special cases that can arise when generating the root table. Now, let's look at the equivalent closed-loop transfer function shown in figure 6.1. Since we are interested in the system poles, therefore, our attention will be on the denominator of the system. Before we proceed with interpreting the table, we first need to create or generate the root table as shown in table 6.1. The question now is how to create the root table. We can actually start with labeling the rows with power of S. We can actually start with labeling the rows with power of S. From the highest power of denominator of the closed loop transfer function to S power of 0. From the denominator of the closed loop transfer function, we can see that the highest power of denominator of transfer function is S power of 4. From the denominator of the closed loop transfer function, we can see that the highest power of denominator of transfer function is S power of 4. Therefore, the first row of the first column must be started with S power of 4. And the last value of S is S power of 0. Next step is to fill in the table with the coefficient. The coefficient with highest power of S in the denominator must be put first. Followed by other coefficient. The coefficient must be rearranged as shown in the table. From the denominator, the coefficient for the highest power, which is S power of 4, is A4. Therefore, the second column of the first row must be started with coefficient A4. The coefficient must be rearranged as shown in table. Now, we are ready to fill in the table. The remaining entries are filled as shown in the slides. Each entry is a negative determinant. Each entry is a negative determinant of entries in the previous two rows. Divided by the entry in the first column directly above the calculated row. Each entry is a negative determinant of entries in the previous two rows divided by the entry in the first column directly above the calculated row. The left-hand column of the determinant is always the first column on the previous two rows, and the right-hand column is the elements of the column above to the right. The table is complete when all the rows are completed down to S power of 0. The table is complete when all the rows are completed down to S power of 0. Table 6.2 is the completed root table. Let us look at the example. Make the root table for the system shown in figure 6.2a. Now, Can you identify the first step should be taken in solving this example? Remember, our interests are in the system poles. Therefore, our attention will be on the denominator of the system. My question is, can we directly use the denominator of this transfer function? Can we directly use the denominator of this transfer function? Yes. We cannot directly use the denominator of the transfer function shown in figure A. Why? Any one of you know why we cannot directly use the denominator of the transfer function shown in figure A? We can't use it because the denominator shown in the transfer function of figure A is not from equivalent closed-loop system transfer function. I repeat, the denominator shown in the transfer function of figure A is not from equivalent closed-loop system transfer function. In order to use the denominator of the closed-loop system, we need to find its closed-loop system equation first. To do so, you must use the equivalent feedback system formula. As learned in the previous chapter, remember G A equal to G over 1 plus minus GH. Figure B shows the equivalent closed-loop system obtained using the equivalent feedback system formula. Now, we already have the denominator of the closed-loop system transfer function. We already have the denominator of the closed-loop system transfer function, which we are interested for, meaning that we are now able to create the root table. Do you still remember the next steps in creating the root table? Yes, the first step or the next step is labeling the rows with power of S. From the highest power of the denominator of the closed-loop transfer function to S power of 0. From the denominator, we can see that the highest power of denominator of transfer function is S power of 3. Therefore, the first row of the first column must be started with S power of 3. The next step is to fill the table with coefficient. The coefficient with highest power of S in the denominator must be put first, followed by other coefficient. And the coefficient must be rearranged as shown in the table. From the denominator, the coefficient for highest power of S, which is S power of 3, is 1. Therefore, the second column of the first row must be started with 1. The next step is to fill in the table. You are now filling the table with the remaining entries as shown in the slide. Remember, each entry is a negative determinant of entries in the previous two rows. divided by the entry in the first column directly above the calculated row. The left-hand column of the determinant is always the first column of the previous two rows, and the right-hand column is the elements of the column above and to the right. Finally, the table is considered complete when all the rows are completed down to s power of 0. Table 6.3 is the completed root table for example 1. Then, the biggest question here is what is exactly the function of this root table? Recall from slide number 12, root heuris is one method used to check for stability condition of one system without the need to solve for the closed-loop system poles. Using root heuris criterion, we can know how many closed-loop poles are in the left half plane, right half plane, and also on the imaginary axis. Okay, please listen to this. The root heuris criterion declares that the number of roots of the polynomial that are in the right half plane is equal to the number of sign changes in the first column. If the closed-loop transfer function has all the poles in the left half of the S-plane, then the system is stable. Thus, a system is stable if there are no sign changes in the first column of the root table. So, how to relate all these statements with root table that we generate just now? Okay, table shown in the slide is the root table that we generate in the example 1, right? From the statement in the previous slide, it says that a system is stable if there are no sign changes in the first column of the root table. This is the first column of the generated root table. This is the first column of the generated root table. The system is unstable if there are sign changes in the first column of the root table, and the number of roots of the polynomial that are in the right half plane is equal to the number of sign changes in the first column. Now, from table 6.3, we can see that there are two sign changes in the first column. The first sign change occurs from 1 in the S2 row, S power of 2 row, to negative 72 in the S power of 1 row. The first sign change occurs here, from positive to negative. So this is the first sign change. And the second sign change occurs from minus 72 in the S power of 1 row to 103 in the S to the power of 0 row. So this is the second sign change. Therefore, we can conclude that the system of figure 6.2 is unstable, since there are sign changes in the first column of the root table. Specifically, there are two pole axes in the right half plane of the S-plane. Try to do this example by your own. The answer is as provided below. You may compare your answer with my answer. Okay guys, and for this week lecture, we will continue part 2 of chapter 6 next week. So, see you next week insyaAllah. Assalamualaikum and bye.